here's problem 2 for homework 12. So now we have the people in 470, a class I teach. They've designed this hoist, this two-stage reduction gear hoist that has a motor and gears A and B connected, and then gears C and D connected, and then that's connected to drum E, and it's supporting this W, this weight, and the radius, the radii of the gears, this is 1.5 inches, and this is 9 inches, this is 1.25 inches, and this is 12 inches, and this drum has a radius of 2 inches. And this motor, interestingly enough, has a motor controller that controls it so that omega is equal to 100 times t plus 4 radians per second. And we want to find the distance that W travels right here. And I think you can ignore that that acceleration right there. Ignore that little arrow. I think I put that in there. I didn't intend that to be there. So anyway, the distance that load W travels after 5 seconds, starting from rest, and the magnitude of the total acceleration of a point on D right here. So I got my nice isometric templates out and made a little sketch of the thing. It helps, and I decided to call this point P, just a point on there, and I want to find the magnitude of that. So that's going to require that I find the tangential acceleration and then also the normal acceleration. So that's something I kind of know from the beginning. And so in part A, I want to find the distance this thing has moved after it has gone for 5 seconds. So what I really want to do, because I know omega is a function of time, right? I know that that's going to be d theta dt. So I can find the number of turns this thing has made, the motor has made after 5 seconds, and then I can work backward or work forwards, I guess, and find the distance this has moved. And if I go by my sketch, let me double check here. I said omega is going this direction right there, right? So let me put that on here. Here's my omega. All right, so I use my little hand principle where my hand's going to get caught in there. So if this is turning this direction, this has to turn that direction, right? What is this number right there for? I don't know. What does that number do? I've never seen that number before. That's weird. Okay, but anyway. So this is turning, let's say that that's turning counterclockwise. So this is turning clockwise. So this one's on the same shaft. So it has to go clockwise, right? So that means this one, my hand gets stuck in there, remember, has to go counterclockwise. So this is actually going downwards. All right. It wasn't really clear from this which way this was going. Right. So that's just something to know. But let's go back to trying to find out the distance. Let's figure out what the angular displacement of this is going to be. So let's even call it. This is going to be at A, right? Because the motor is going to be the same as this. So we'll just go ahead and put that in there. So let's say that we're going to have d theta of A is going to be equal to omega A dt, which is going to be, and we're going to integrate that starting at 0 to some time, and starting from, let's just say, an angle we could call theta to some theta. Right, so this is really just going to be delta theta, what we're going to find it there. And so putting this back into there, now we're going to put in 100 t plus 4 dt. All right. So yeah. So we're going to have this delta theta, right? That's all I'm going to say that thing is right there. And we're going to get, let's call it 50 t squared plus 100 times 4, right? So that's going to be 400 t. Anything else? No. And this is really going from 0 to t, right? So that's going to be the answer right there. And so at t equals 5 seconds, delta theta, well, I should have made that A. Brain's not working. We're going to say at 5 seconds, we're going to have 25 times 50, boom, and then have 400 times 5, boom. So we have 3,250 radians. All right. So, that's an interesting result there. Do I want to go? We're going to need the acceleration right here, which we happen to be able to also find right from this right here. We can do this in one, or we could come back and do it later. Let's go ahead and find the amount of distance this thing has moved now that we know this amount of radians right here. So we can say that the distance these two have in common right here, we go theta b. I guess I'm gonna go RB times theta b is equal to RA times delta theta A. So we can have delta theta b is going to be RA over RB delta theta A. I want to keep the delta in there. So let's see, that ends up with A is 1.5 and B is 9. And this is 3,250. So we're going to have 1.5 times 9 divided. We get 541.7 radians. Right, and now we got to go. Now we know that delta theta C has to equal delta theta B because they're on the same shaft. They turn the same number of times. So we're going to say RC delta theta C is equal to RB delta theta B. So therefore delta theta C is RB divided by RC delta theta B. And the radius of B is nope. Darn you. Can't go back in time. I'm not going to shoot. Okay, this D. That's the one we're worried about, right? That they share the same thing. I was going on autopilot. I had that C and this B right there. So this is going to be D, and that's going to be D. So we're going to take the radius of D, which I keep messing things up, man. That's why you shouldn't be transcribing. Don't transcribe. Watch me. Watch the thing only after you need help. This is going to be D. So that's going to be RC over RD delta theta C. Did I do that right? Yes. So we're going to have 2 over 12. So the radius of C is 2. This is 12 times our 541.7. So I get this one is going to be equal to a 2 times 12 divided. And so we get 90.28 radians. And lastly, we know that delta theta E equals delta theta D, right? And so which equals 90.28 radians, right? So delta YW is going to be RE times delta theta E. So that's going to be 2 inches times 90.28 radians, which comes out to 180.6 inches, and divide it by 12, so we get 15.05 feet. Gotcha. Okay. So hopefully I didn't make that too big of a mess, but you're seeing what I'm doing is the distance that these outside perimeters move has to be, the distance this outside perimeter moves has to be the same as this. That allows us to have this relationship right there. Now we also want to find the acceleration of this thing right here. That means that we're going to have to get the velocity too. All right, so there's a couple of things that we're going to need to do. We need the velocity and we need the acceleration. So let me get the acceleration. Let me do the velocity next, right? So this is the position of the thing. Now let's look for the velocity. All right, so I'll write at the top here. We did position. So let's go through the velocity. So at t equals 5 seconds, omega A is equal to 100, let's see, times 5 plus 4. And I should be able to do that in my head. That should be 900 radians per second. All right. So going through the same thought process here, we have omega. Let me go R's first. I'm going to try to be consistent with that. I don't know if I have. I probably haven't already. RA omega A is equal to RB omega B. Therefore, omega B is going to be RA over RB times omega A. So, and it reduces it, right? So it's 1.5 over 9 times, where'd you go? 900. So 1.5 over 9 times 900 comes out to 150 radians per second. All right. Now we know that omega C has to equal omega B. Therefore, and we know that we have to have RD times omega D has to equal RC times omega C. And we know omega C because we know that's equal to this right here. So we say that omega D is equal to RC over RD omega C. C is going to be 1.25, D is 12, and omega C is 150. So 1.25 times that, 12 divided by that. Now we're all the way down to 15.63 radians per second. Now that's all we actually need to know for this question. Yeah, we only need to know that because we're only looking for a point that's on D. So now we have what omega D is going to be. All right, so the next thing we need and this is going to be page 3, and this is 2 continued, is now we need to do acceleration. And we know that acceleration is d omega dt. So we have, that's going to be d dt of 100 times t plus 4. So we have the and this is the acceleration of A. Acceleration of A is therefore going to be just equal to 100, right? 100 radians per second squared, because take the derivative of that, that's just 100. All right, so we want to get the accelerations now of all of these things. So I'm going to start with the same process. RB times the acceleration of B is RA times the acceleration of A. Therefore, the acceleration of B is RA over RB, acceleration of A. Or 1.5 over 9 times 100. 1.5 divided by 9 times 100. So that should be 16.67 radians per second squared. And then we know that acceleration of C is equal to the acceleration of B. So we take the acceleration of the R times acceleration of C equal to RB times the acceleration of B. And we can find that the acceleration of C is going to be RB over RC, acceleration of C. And so that's going to be, let's see, did I say that wrong? I did. Son of a bitch. Turn my brain off while I'm trying to talk. It's hard to talk and do this at the same time, by the way. All right, so we know that right there. But this right here, we're going to say D and C, right? Because that's the thing we're really doing. We're connecting these two together. So that's the reason why I want to put it there. So we have the acceleration of D, that's what we want, is going to be C over D times C. And so that's going to be 1.25 over 12 and times 16.67. And we're going to end up with 0.25 times 12 divided 1.736 radians per second squared. Okay, so we're all set now. We're going to take a look at what happened to... Okay. I'll draw a little guy here. This is going to be D right here, right? Maybe I'll make it a little, the center of them. I didn't center that thing correctly. Let's see here you go. There's the center of this, and we're going to have the acceleration of D in the tangential direction and the acceleration of D in the normal direction. So the acceleration of D in the tangential direction is going to be alpha D times RD, right? And so that becomes 1.736 times, what did we say D was 12? Right, so that's going to be 20.83, these inches per second squared. The acceleration of D in the normal direction is going to be omega D squared RD. Whoops, come on. So that ends up coming to That was from the previous page, 15.63. So it's going to be a bigger number, times 12. And so 15.63 squared times 12, much larger number, 2,932, call it, inches per second squared. So the acceleration of D, or the acceleration of a point on D, I should actually say P. So these should all, I should all change all of these to P. That's the reason why I made the thing right there. P. That's why I made a point called P. I shouldn't make videos anymore. I should just give up. That's all right. We'll say that it's 20.83. And this is so small compared to the other one that it's probably not going to change hardly even noticeably. But let's try it anyway. That squared and that squared and add them together. And sure enough, didn't change at all. 2,932 inches per second squared, right? Which almost may be better to do in feet per second squared. But let's hear. Here's the answers. A is going to be, what were we asking for? Delta W, delta Y W. Delta Y of the weight is going to be, where'd you go? 15.05 feet. Yeah, I decided to put it in feet. 15.1 feet, and we said it was going down. And then B, the acceleration of P, magnitude 2,930 inches per second squared. Actually, I probably should turn that into feet here, right? Let's just divide by feet. So we get 244.3 feet per second squared. And you might actually notice there's something seriously wrong there. That is way faster than the speed of gravity, right? So it's going to be hard to make that bucket like drop fast. Like the bucket, the rope is going to go in. The rope's just going to come flying off of the thing because the bucket can only go 32.2 feet per second squared down. So the rope is going to come off of the thing. All right, so our problem has fallen apart. But it was mostly the concepts behind the thing. I'd like to have real numbers, but it's actually kind of interesting when you get something that's absurd. I'm like, yeah, that can actually happen. All right. I should ask questions like, what is wrong with this? And then have you come up. All right, that's it. Let's see, how do we do? 23 minutes, whatever.